My dear student friends, I hope you understood the last two lectures, and by this time you know what is the importance of a separation process, why a separation process is required, and what happens if you don't have any separation process, and what are the recent trends that are going on in the separation process, what are the applications of a separation process. Then we have seen about classifications of a separation process, and for a particular application, if you have several of the separation techniques and which separation process that you have to select it, and then what are the challenging tasks for the being a chemical engineers, what are the things that we can do in the separation process. Now in today's class, what we are going to discuss about how we have to conduct the separation process, and that is what we call it as the methods of conducting a separation process. And these methods can be a steady state process, or it may be unsteady state process. And all of you know about the steady state. If anything which varies with the time, which we call it as the unsteady state, if anything which is not going to vary with the time, that we call it as a steady state. So this separation process can be carried out either in the steady state process, that is what we call it as a continuous processes, or we can conduct the steady state processes, separation process in unsteady state fashion, that may be in the batch process, or it may be a semi-batch process. So the device that we need to conduct a separation process, we call it as a stage, and a stage is a device or a combination of devices in which two soluble phases are brought into contact. When you bring these two phases brought into contact, mass transfer is going to occur between the phases. Then the two phases are separated mechanically. The entire this unit, we call it as a stage. A stage is a mechanical device where the two phases are brought into contact and allowed sufficient time. Then the two phases are separated mechanically, and during this process a component will be transferring from one phase to the other phase, and this entire thing we call it as a stage. And we can have very good example here, a distillation process, and let's say we have a solution of ethanol and water which is coming from a fermentation process, assuming that we have 6% concentration of ethanol, and when we want to use for the drinking applications, maybe we need to have around 40% of the concentration of ethanol. Then what we do is we will pass this feed solution into a separation unit, or what we call it as a stage. There we supply the heating. When you supply the heating, we have a more volatile component, that is what we call it as the ethanol. We have a less volatile component, that is what we call it as the water. Now depends on the volatilities, ethanol will vaporizes, water also will vaporizes, but in a different proportions. So when you say we are going to get here a vapor phase, and here in the vapor phase we have both ethanol and water, but in a different proportions. Your thermodynamic is going to, the vapor liquid equilibrium diagram of a thermodynamics is going to gives you, when you take a 6% of the concentration, we may get around 33% concentration of ethanol and 67% of water if thermodynamic equilibrium is established between the vapor phase and the liquid phase. But as you know, no stage is the ideal stage. Generally the stage we can take it as the ideal stage, which we can take it as a standard reference, and no system attains the equilibrium. So we won't get a 33% concentration. Maybe let's say we get around 25% concentration. Exact calculations, whether it is 25% or 33% or 30%, whatever it is, that we are going to learn from the thermodynamics. That is when you are going to read about your vapor liquid equilibrium diagrams. And if you know the concentration of ethanol in the feed solution is 6%, when you subject it to the vaporization process, or when you subject it to a distillation process, we may get around 33% concentration if the system attains the equilibrium. For a system where 1 atmospheric pressure we have. If a system doesn't attain the equilibrium, then we get around 25% of concentration. Now this 25% will not be sufficient. So what we have to do, we have to do further separation. The further separation can be done by passing this vapor phase into a condenser, where the vapor phase is going to be condensed, and we can call it as the two types of condensations. We call it as a total condensation, or we can say partial condensation. In the case of total condensation, the entire vapor is going to be converted into the liquid. And when we have around 25% of ethanol, and when you take that ethanol and when you do the total condensation, we are going to get again 25% of liquid phase of 25% of ethanol and maybe 75% of water. As I told you, you have to be very clear, this exact concentration is going to depend on the thermodynamic, and it is also going to depend on the stage efficiency, and it may be too difficult to understand about these concentrations. But when you are going to read about your vapor liquid equilibrium diagram, when you are going to understand about your stage efficiency, then one can know what is the concentrations of ethanol, exact concentration of ethanol and exact concentrations of the water. Now when you take this ethanol and water, again when you do the heating, and again if equilibrium is going to be attained, maybe 44% of ethanol, and maybe we can have around 56% of water we are going to get it. Now this 44% of ethanol and 56% of water, again if the system is a equilibrium system, or if the stage is the equilibrium stage, otherwise as I told you, no stage is the equilibrium stage, and we may get at 44% or 44%, or you may get less than this, and what we can do, we can pass it to the again condenser, and we can get the condensed liquid here. And when you do the condensed liquid, maybe we have around, depends on the stage, we may get around 40% of ethanol, and this 40% of ethanol will be sufficient for the drinking applications. Now here we are going to get something, and here we are going to get something, and here this 40%, if this concentration is sufficient, we can stop the process, or otherwise what you have to do is you have to pass it to the third stage. Again we apply heating, again the vapor phase is going to be created, so that way this process is going to be continuous. And if one can observe, we can observe that wherever we have to supply the heat, we are supplying, wherever you have to remove the heat, we are removing the heat. But in the real processes, because of the energy conservations and other things, we cannot do this sort of a thing, and there we have to go for the continuous process, or what we have to do is we have to go for a system called as the cascade system, where in the cascade system, where a series of stages are combined together, that we call it as a cascade. A series of stages are combined together, and we call it as a cascade, and the phases are going to flow from one stage to the other stage. And in the cascade systems, we may have three types of things. One we call it as a cross current, we have a counter current, and we have a cross current, co-current. We have a cross current, we have a counter current, we have a co-current. And just to clear up more about this sort of a cascade system, maybe what we can do, you can imagine how the villagers are going to prepare the alcohol in the villages. Particularly this was the case when the government has banned the selling of the liquor in the open shops. What these villagers has to do, they used to have maybe three types of a farting system. They have a pot here, and here they have taken some sort of a water, they have taken some black jaggery, and they have taken some sort of a salt. Then they applied the heating here. When they apply the heating here, now you are going to get the fermentation process is going to take place. After fermentation has occurred, again the vapor phase is going to be created because of the volatilities, and when the fermentation takes place, so your black jaggery is going to be converted into the alcohol now, and this alcohol is vaporizing because it is a more volatile compared to the water. So we are going to have the vapor phase. In the vapor phase, we have a high concentration of ethanol as compared to the concentration of ethanol that we get when you do the fermentation. So when you take a vapor phase, we are going to have the ethanol, we are going to have the water. Now as I told you, if stage is this part, if the part is assumed as the equilibrium stage, we may get around 33% concentration of ethanol, maybe a 67% of water, but no stage is the ideal stage, and what we are going to have concentrations which are less than the equilibrium concentrations. So maybe if we can assume that you may get around 25% of the concentration and 75% of water, then what you have to do, maybe we can pass it to the second stage, and in the second stage nothing but we have a second part, and the vapor phase, whatever it is formed, that will goes to the pores of the second part, then condenses, it becomes a liquid. That is, the total condensation is going to take place. Still we are going to apply the heat, and because of the heat, a part of the liquid is going to be converted and it is going to form the vapor. And this vapor, maybe we have around 40% concentration, and this is dictated by the thermodynamics, and we, on the top of it, we are going to keep the third stage, or maybe we call it as a third part, and in the third part the liquid goes and condenses, and what one can do, we can stop the process, and when you are going to collect this ethanol, it may have around 40% of the concentration, and that is sufficient for the satisfying the desire of the human beings. So what I want to tell you here, if you can observe the difference between this and this, here in this case, wherever we have to supply the heat, we are supplying; wherever the heat we have to remove, that we are removing the heat. But for the energy conservation, we cannot go for this sort of a thing, and here one can observe that we are going to apply the heating at only one place, and the phase, the vapor phase, is flowing from one stage to the other phase. When it goes to the second part, it becomes a liquid. Then again vapor is going to be created. Again it is going to be converted into the liquid. And if you are going to keep another part, then the liquid is going to be converted into the vapor. Or what we can do is, we can stop the process there. We can stop the process because we are going to get the desired concentration of 40% of alcohol. This is what the villagers are going to do. When you, maybe this is the thing that we observed when you are going to see some movies where the people have prepared the alcohol, and they satisfied their design. And one more important thing that you have to understand, the process parameters are going to make some important thing in the formation of the alcohol. Suppose if you are not going to control your process parameters properly, maybe that is about the concentration of your black jaggery, maybe concentration of your salt, maybe a concentration of water, and if you don't supply the proper heating, then sometimes what will happen, the fermentation process may give rise to ethanol. That is nothing but A gives rise to ethanol. At the same time, the fermentation process may also give rise to methanol. So if we are going to get the ethanol, and if we are going to get the methanol, and methanol is a more volatile component when compared with the ethanol, the vapor phase contains more amount of methanol, and this again vaporizing, again this liquid now contains more in methanol, and this vapor again contains more methanol, and this liquid contains more methanol. So what will happen, if you are not going to control your conditions properly, then what will happen, A may be the fermentation process may give rise to ethanol, the fermentation process may also give rise to methanol, and the methanol concentrations will be very, very high in the top part. As you know, the methanol is one of the things that is used in the industries as a denaturing agent. The purpose of the denaturing agent, and suppose if you have the barrel of alcohol, maybe the people who are working in the industry, they may be tempted to drink such type of alcohol. To avoid such type of problem, what we do is, we deliberately are going to add the methanol or the benzene into the ethanol, and if one can see that, and on the top of the barrel they write it as denaturing agent is added. If one can see that the denaturing agent is added, nobody is going to take such type of methanol, or such type of alcohol. So what I want to tell you, if the process parameters are not properly maintained, then there is the formation of the byproducts, maybe a methanol, and this methanol concentrations will be very, very high in the top part, and if you are going to drink such type of liquid, people may die. And this is what the problem of recent Milevaram problem, where people have prepared the alcohol in the villages, they were not able to control the conditions properly, and the final alcohol contains methanol. The villagers are not known about the presence of the methanol traces, and and they consumed it and they died. So what I want to tell you, the chemical engineers are going to play an important role in the society, where they knows a lot about reaction engineering, they knows about the separation process. If your conditions are not proper, if your separation process are not proper, there is a chances of killing the people. So this is where we have to understand about the importance of the chemical engineering profession, and maybe this gives you an example where how a chemical engineer is going to be useful for the society. And this is what I want to tell you. This is the difference between this and this, where we have a continuous heating and continuous condensation, but here you are going to do the only one place we are going to do the heating, and this is what we call it as a continuous process, or we can call it as a group of stages we are going to use, and this group of stages we call it as a cascade. And now in the cascades, as I told you already, there is a cross current cascade, or maybe a counter current cascade, and you have a co-current cascade. In the case of cross current cascade, so we have a one stage, we have another stage, we may have a third stage like this. So now what is happening, the one phase is flowing from one stage to the other stage, that is stage 1, we can call it, maybe you can call it as a stage 2, we can call it as a stage 3, we can call it as a stage 4, stage 5. And here the second phase, phase 1, is flowing from one stage to the other stage, whereas the phase 2, a fixed quantity of phase 2 is added into the stage 1, and the phase 1 and phase 2 are brought into contact. The mass transfer is taking place between the phases, and then the phases are going to be separated mechanically. Then here we are going to get the phase. This phase contains different in concentrations when compared to the phase what you added here. Now this phase here coming here, again it will have a different concentrations that will goes into the second stage. Again we are going to add some fresh amount of the phase 2, and then again the separation is going to take place. Then this goes phase, this phase again comes here, and again we are going to add some more amount of phase and some more amount of liquid or whatever it is. Then again, so what I want to tell you, one phase is moving from one stage to the other stage, whereas the second phase is added into the stage 1 and allowed for sufficient time. The mass transfer is taking place between the phases, then the two phases are separated mechanically, then the phase 1 is flowing into the second stage, phase again which is brought into contact with the new quantity of the phase, and again the mass transfer is taking place, it goes into the third stage, etc., etc. So this is what we call it as a cross current operations, and how many stages we have to use, and that depends on the what is the concentration that we are interested to get it at this location. And then we have another type of operations, we call it as a counter current operation. Here we have a stage 1, here we have a stage 2, maybe we have a stage n, and here one phase is flowing like this in one direction, the other phase is flowing in the opposite direction, the other phase is flowing in the opposite direction. Maybe this is stage 1, stage 2, maybe this is the stage NP. That means there are the NP stages are there. This is what we call it the counter current operation. The two phases are flowing in the opposite direction, and in the stage they are going to be brought into contact. The mass transfer is taking place between the stages, and this is what we can say. Then the third operation, what we can call it as is a co-current operation. In the co-current operation, we may have it like this, and now this is the both phases are flowing in the same direction. This is what the difference between the counter current operation, cross current operation, and a co-current operation. And here again we have a stage 1, stage 2, there is a NP stage. The phases are flowing in the same direction, the mass transfer is taking place between the phases, and this is what we call it as a co-current operation. And maybe at the later point of a time we are going to understand, we are going to discuss more about this counter current, cross current, co-current operations. Then the next question comes into the picture, and this is the how we have to keep the stages in a tower, and this may be tray towers or it may be a packet towers. And in the case of tray towers, the continuous operation is possible with the tray towers, or the continuous operation is possible with the packet towers. In the case of tray towers, we have a tray, we have a vertical column, and this vertical column contains the different plates, and that each plate we are going to call it as a tray, and the liquid is coming from the top of the column and the gas is coming from the bottom of the column, and the bottom goes into the pores holes of this tray, and gas is, liquid is flowing down like this. This is what we call it as a liquid hold up, and when the gas goes up here, the liquid is coming down here, the mass transfer is taking place between the two phases, and the liquid is coming down because of the gravitation forces, and the gas is flowing up because of the buoyancy forces, and the two phases are brought into contact on this tray, and the next contact is going to occur on this tray, next contact is going to occur on this tray, next contact is going to occur on this tray, and this is what we call it as a tray towers. Then we have another tower that we call it as a packet tower. In the case of packet tower, we have a tower, maybe here we have a support, and we have some packing restrainer, and here we are going to have some packing materials. Here we have a packing materials, and now the liquid is flowing down and the gas is going up, and the mass transfer is these two phases are brought into contact over the packing material, and the two phases are leaving, and the next contact is going to occur here, the next contact is going to occur here. So continuously over the packing materials, the two phases are brought into contact, the mass transfer is going to take place between the phases, and this is what we call it as a packet towers. And now when we talk about this separation process, and which is based on the principles of mass transfer operations, and before entering into a mass transfer operation, one should understand what is my objective, and my objective is to design about my tray towers or the packet towers. So the design is the most important thing, and design is basically is a job of a chemical engineer in the process industry. And in the design, the various objectives we have, that is estimation of the equilibrium stages. As I told you, a very good example of your preparation of alcohol in the villages, you may keep the 2 parts, you may keep the 3 parts, you may keep the 4 parts, depends on what the concentration that we are going to expect, and that is what we call it as the equilibrium stages. And this equilibrium stages is given by the thermodynamics, and your material balance is also going to help us calculating the equilibrium stages. Then the next thing is the time of contact. Another important parameter, that is nothing but the time of contact. This time of contact, and this time of contact is going to depend on the in the case of a batch operation, the time of contact will tell us how much of mass transfer has occurred. In the case of continuous process, the time of contact will help us to know how much of cross section area that has to be provided for the either tray towers or the packet towers. Then the next thing is the flow rates. What are the permissible flow rates of the liquid or the permissible flow rates of the, and your fluid dynamics is going to help us to know about the permissible flow rates, and your material balances also will help us to know about the permissible flow rates, and your cross section area. By knowing about the flow rates, one can estimate the cross section area. Then the fourth important point thing is the energy requirement. And as you know, one of the important thing in the process industries is the energy. How much of energy that you have to supply. Energy may be needed in several forms. One may be increasing the temperature, that maybe we have at 30 degrees centigrade, and we may have to heat the solution up to 50 degrees centigrade without changing phase. Then what one can do, we can use the equation of MCP delta T, and we can calculate what is the energy requirement. That is what we call it as a sensible heat. Or in sometimes we may have to change the phase, and when we have to change the phase, what is the energy requirement. So maybe for example, when you talk about I have a liquid water at 30 degrees centigrade, I want to get the vapor water at 110 degrees centigrade. So what we have to do, we have to supply the heat for converting a liquid water at 30 degrees centigrade to liquid water at 100 degrees centigrade. That is what we call it as the MCP delta T. That is what we call it as a sensible heat. Then we supply some more energy to convert the liquid into the vapor at 100 degrees centigrade. So now once after getting the vapor, so now that vapor has to be heated again from 100 degrees centigrade to 110 degrees centigrade. So some more amount of sensible heat is required. So sensible heat required to heat the liquid from 30 degrees centigrade to 100 degrees centigrade, and there is a latent heat is required to convert the liquid water into the vapor water. Then again we need some sort of a sensible heat to convert the vapor which is at 100 degrees centigrade to 110 degrees centigrade. So this is what one of the energy requirement in the process industry. And this is not only the energy, and we may need some energy for running of the pumps, because as I told you already, the liquid is flowing down, the gas is flowing up. Maybe in between we have to increase the flow rate, or we may have to decrease the flow rate, or we have to do something. If we want to do that, then we need some sort of a pumps, and we need some energy to drive the pumps. Then we may also need some sort of energy for mixing of the materials, like if I take a gas phase and if I take a liquid phase, if I don't provide the proper mixing, then what will happen? There is no proper contact between the liquid and the gas, and no proper mass transfer is going to take place. So to provide the proper mass transfer, what you have to do, we may have to stir it, and when you want to stir it, we need some energy for the stirring purposes. And not only that, sometimes we may need energy for the dispersion things. So what I want to tell you, our energy is required in several ways, and one has to calculate what is the energy requirement in the separation process. And not to exaggerate, not to tell you, but the thing is, most of the separation process are selected only based on the energy requirements. And this is the what about the design. And being a chemical engineer, you should know how to design what are my design parameters. In the case of tray towers, you may have to estimate the number of stages. In the case of packet towers, you may have to estimate what is the height of the packet towers. Finally, your number of stages or the height of the packet tower is going to depend on the how much of separation that is required. So one has to consider about these things, and one has to design the separation process. So by this time you understood about what exactly you are going to do in the separation process. And when the separation process has to take place, the mass transfer has to occurs within the phases, or the mass transfer has to occurs from the phase 1 to the phase 2. So now the next question comes into the picture, how the mass transfer is going to take place. And for that, what we are going to discuss in first few modules, we are going to discuss about how a gas particle or a liquid particle or a solid particle is moving from the one location to the other location, or why actually the mass is transferring from one location to the other location. That we are going to start, and that is what we talk about molecular diffusion in fluids. Actually, what is this molecular diffusion, or what is this mass transfer? And before to talk about something like this, and just I want to give you one more example. Now people talk about, there are two types of technologies people talk about. One we call it as a cleaning technology, other one we call it as a clean technology. And in the case of cleaning technology, what will happen? So, already the site is contaminated with the effluents, then we use some sort of a technology to clean that effluents. That is what we call it the cleaning technology. In the case of clean technology, what we do is we will see that we are going to incorporate a separation process in the process industry or in the reaction, so that no effluent is going to be discharged, or what we call it as a zero effluent discharge. And that is what we call it as a clean technology. But of course, when you want to convert a cleaning technology into a clean technology, we have to spend a lot of money, and your money is one of the important issue, and so much of money that you have to invest to convert a cleaning technology into a clean technology. But now government is putting so much of restrictions on the environmental engineers, asking them to convert all the cleaning technologies into the clean technologies, and these separation processes are going to play an important role to maintain your environment so nicely. And when we talk about this, and the mass transfer is the most important thing. And by this time you know something, what is this mass transfer? When we see, if I bring some bouquet of flowers, and if I keep it on a table, and after some time you are going to feel that there is some smell, and that smell is taking place, or that smell, we are able to feel that smell because the mass transfer is taking place from higher concentration to the lower concentration, or the molecules of your fragrances are moving from higher concentration to the lower concentration. Or maybe one more example we can think about. Suppose if you are filling the petrol in a car and you see the smell of the petrol, the reason is there is a petrol is answering from the filling tank to your nose, and because of that the mass transfer, because of that you are able to feel it. So this is what we call it as the mass transfer operations. So the mass transfer operations are going to take place whenever we have a concentration difference is there, and whenever we have the concentration difference, the mass is transferring from one location to the other location. That is what we call it as a mass transfer. Or for the mass transfer to occur, the molecular diffusion in fluids are important, and this molecular diffusion is going to take place by virtue of the thermal energy. As all of you know about the kinetic theory of gases, the kinetic theory of gases says each molecule is having some sort of a kinetic energy of the translation. And when a molecule is having some sort of a kinetic energy of the translation, the molecules are moving from one location to the other location with your kinetic energy of the translation. And now suppose if I assume a vessel, this vessel contains a particular molecule like a X, and maybe we have a particular molecule like a Y, maybe we have a particular molecule like a Z, maybe we have a molecule like A. So now each molecule is having some kinetic energy, and this kinetic energy is going to depend on the temperature. And this molecule, because of this kinetic energy, the molecule is moving in this direction. And what your kinetic theory of gases says that the molecules are always moving the straight line path. But at the same time, this molecule is also moving in the direction. And these two molecules now collide each other, or there is a collision between these two molecules are going to take place. When the collision has occurred, now the direction and the velocity of the molecule is going to change. For example, the velocity of the X is going to changes, the velocity of the Y is going to changes. Now what will happen? This X molecule will take a diversion, little direction change, and it will lose some velocity, maybe it gains some velocity, and it is going to move in this direction. Now at the same time, the A molecule may be moving in this direction, the Z molecule may be moving in this direction. There may be a collision between the molecules here, and the A molecule may change the direction change, and the Z molecule may change the direction change. So now this X molecule is coming like this, your A molecule is coming like this, again there is a collision between the molecules. And because of these collisions, and maybe the X molecule may come back to the original position, or may go in the forward direction, may go in this direction, may go in this direction, any direction it can go. So what I want to tell you, the molecules are always moving from one location to the other location. When they are moving from one location to the other location, there may be a collision between the molecules, and when these collisions are going to occur, then there may be a change in the direction, there may be a change in the velocity. And now if you are going to see, we are going to call it a one parameter. That parameter we call it as a mean free path. This is the most important property, or the most important thing in the mass transfer operation. Mean free path is the distance traveled by the molecule before collision to occurs. Right? And the X molecule is moving in direction, the Y molecule is going to be moving in direction, and they have traveled for certain distance, then the collision is going to be occurring. And this mean free path is going to depend on, and this mean free path is defined as what is the distance traveled by the molecule before collision to occurs, that we call it as a mean free path. And this mean free path, obviously it is going to depend on the pressure, and this is going to depend on the temperature. So suppose now if you are going to decrease the pressure, then what one can see, the number of molecules, the pressure is decreasing, the pressure is less, means the number of molecules in a given volume is less. When the number of molecules in a given volume is less, number of collisions are going to be less. When the number of collisions are going to be less, the mean free path will be more. So this mean free path, we call it as the lambda. This lambda is going to be increasing when the pressure is going to be decreasing. And at the same time, when you increase the temperature, then what will happen? The kinetic energy of the translation is going to be increasing. The molecules are going to travel for a longer distance. Then the collision is going to take place. So that means the lambda is going to be increasing with increasing of the temperature. So the mean free path, that is the distance traveled by the molecule before collision to occurs, is going to be increasing with decreasing of pressure, or maybe increasing of a temperature. Then what we call it as the most important thing again is the rate of diffusion. And this rate of diffusion, as I told you, if you observe the molecule of X, this molecule of X has traveled in this direction for certain distance, then the directional change has taken place, then the direction is going to be occurs. So if you are going to look at the molecule of X, in a given time, the molecule of X is traveled only this distance. So what one can say, the next distance traveled by the molecule in a given direction, in a given time, we call it as the rate of diffusion. This is a very, very, very slow process. Try to understand the thing what I am trying to tell you. So here we have the molecule of X, the X molecule moving in the direction, and the collision is going to be occurs. There is a directional change, and the molecule of X is moving now in this direction, then the molecule of A is coming like this, and again there is a collision between the molecule. The X molecule may move in the several directions, or maybe assuming that this is moving in this direction. If you are going to look at this, the net distance traveled by the molecule of X in a given direction in a given time is only this distance, and this distance is very, very small when compared with your mean pre-paths and other things. And this net distance in a given time in a given direction, we call it as the rate of diffusion, and this rate of diffusion is a very slow process. Again, to tell you, this rate of diffusion is going to be decreasing with increasing a pressure or decreasing of a temperature. So the rate of diffusion is going to be increasing with the decreasing of P, or maybe with increasing of T. The rate is going to be decreasing with P, and it is going to be increasing with T. And for example, if you take a system of evaporation of water at 25 degrees centigrade, and if you are going to maintain the total vacuum, that means there is no pressure. We are going to maintain complete vacuum, and one can observe that there is a 3.3 kgs per second of water is going to be evaporated. 3.3 kgs per of water is going to be evaporated per every second at 25 degrees centigrade if you are going to maintain a vacuum. And suppose if you are going to put a stagnant air over the liquid pools of a thickness of maybe a 0.1 mm thickness, and this rate now is going to be reduced by 600 times. So now you can understand the importance of the pressure. What I am trying to tell you, if you are going to maintain the vacuum at 25 degrees centigrade, if you are going to maintain, the water is evaporating. For every 1 second, there is 3.3 kgs of water is evaporating. Just if you are going to put a stagnant air over the liquid water with a thickness of 0.1 mm, the rate of evaporation of water is decreased by 600 times. So this will show us about the molecular diffusions are very, very slow, and these molecular diffusions are going to be reduced further by increasing the pressure, and this molecular diffusion may increases with increasing the temperatures. And now this molecular diffusion, as I told you, this is a very slow process, and uniform concentration in a given vessel we are going to achieve because of the molecular diffusion. For example, if I have a vessel, and in this vessel we have some copper sulfate, and now if I put a water on the top of the copper sulfate, within no time, that depends on the how fast the diffusion is going to take place, there is a uniform color in the entire vessel, or the water color is uniform. And why this water color is uniform? Because of the molecular diffusion of a copper sulfate into the water, water into the copper sulfate, and one can achieve that your uniform color, we are going to achieve it. So this will show us about whenever you are going to bring two phases brought into contact, if the concentration difference is going to be existing between the two phases, then the molecules are going to move from one phase to the other phase entirely. The system will bring it to the uniform concentration, and the system will become a single phase, and the concentrations are going to become uniform. And a very interesting example one can observe, like all of you know the importance of the sugar water, and we would like to have the sugar water maybe in the summer season, or maybe any season we would like to have sugar water. And maybe I don't know whether you observed it or not. If I take a glass of water and if I put a spoon of sugar in that, if I don't stir it, and then what will happen? There is a high sugar concentration at the bottom, there is a low sugar concentration in the top of the water. Now the sugar molecules are moving from bottom to the top, and ultimately the concentration of sugar is going to become uniform. And again, to tell you, the process is very, very slow process. It takes a long time to get the uniform concentration. And for example, if I take a salt, maybe some amount of salt if I am going to take, and if I am going to put water without disturbing the salt, that is, if I put a carefully some amount of water on the top of the salt, then what will happen? The salt now will move from higher concentration to the lower concentration, and the water will move from higher concentration to the lower concentration. Ultimately the system is going to come to the uniform concentration. And if you take this is the top surface of the water, and to get 85% of salt concentration over the top surface, we get around 10 years time. 85% of the salt concentration on the water surface, it takes around 10 years time, and to get a 99% of salt concentration, 99% of ultimate concentration of salt over the water surface, it may take around 28 years. So this will clearly indicates how the molecular diffusion, how slow this molecular diffusion. So this is going to give a very interesting example, very good example where the process is going to become very slow. Instead of that, I can use some sort of a paddle agitators, and now I can take this paddle agitators. I will rotate this paddle agitator with 22 RPM. That is a very slow speed. So 22 revolutions per minute. If I am going to stir it, within 60 seconds, I am going to get the uniform concentration. So what has happened here, when you are going to stir the material, there is the formation of the eddies, or we call it as chunks. There is a formation of the eddies, or there is a formation of the chunks. These eddies or the chunks are moving from one location to the other location. When they are going to move from one location to the other location, they are going to carry some amount of solute with them. This eddy will carry to some solute along with them, and after going to the new location, solute will be moving from the eddies into the bulk of the liquid by again molecular diffusion. So whatever, because of this small revolution, small stirrer speed, lot of eddies are going to be generated, lot of chunks are going to be generated. These eddies or the chunks are going to be carry the solute along with them, and when it goes to the new location, it will disperse the solute into the bulk of the liquid, and because of this, the mass transfer is going to be very fast. That is the reason within 60 seconds we are able to get the uniform concentration, and this is what we call it as the turbulent mass transfer. So turbulent mass transfer, or we call it as the eddy mass transfer or turbulent mass transfer. So this turbulent mass transfer or the eddy mass transfer is a very fast process. Within no time you are going to get the uniform concentration. So this is the one example. It gives you the importance of the turbulent flow in the mass transfer operations, and that is where we have to understand about the momentum transfer when you want to clearly understand about the mass transfer operations. Then till now, what we understand, here we have a salt, here we have a water. There is a high concentration of salt here, there is a low concentration of water. The salt is moving from higher concentration to the lower concentration, and ultimately the system is going to become a uniform concentration. But to tell you, this is sometimes concentration is not the driving force for mass transfer operations. We are going to come across a new parameter, that is what we call it as the chemical potential. And this chemical potential, a new parameter, we call it as the chemical potential, and in this chemical potential is nothing but mu, and this is nothing but dou Z by dou Ni, that is change of Gibbs energy with change in number of moles of component I, keeping temperature, pressure and J as constant. So how this Gibbs energy is going to change us with respect to change in number of moles, that is what we call it the chemical potential, and this chemical potential is the driving force for mass transfer operations, not the concentration is the driving force for mass transfer. And to give you one example, we have a process of absorption, and in the process of absorption we have air and we have ammonia, and this is contacted with the water. When you contacted with the water, there is no concentration of ammonia in the water layer. The ammonia will be transferring from ammonia layer to the water layer. And at the same time, the air wants to move from higher concentration to the lower concentration, but thing is, there is no solubility of air in the water, so air will not move into the water phase. And at the same time, water wants to move from water layer to the air layer, but the temperatures we are going to maintain very low, and the evaporation can be neglected. So ultimately what is happening, when I have a gas mixer, that gas mixer contains air and ammonia. If I am going to contact it to the water, and ammonia will be transferring from the gas phase into the liquid phase. Now ultimately what will happen, so the process is going to stop. So the process is going to be stopped means we are going to get the equilibrium. We are going to get the equilibrium means, and macroscopically there is no change, but microscopically still there is some change. That is what we call it as a dynamic equilibrium. And in the chemical engineers, we are being a chemical engineers, we don't talk about a static equilibrium. So we are going to talk about only the dynamic equilibrium. So in the case of dynamic equilibrium, a particular molecule, if you are going to identify X, this X molecule sometimes may be there in the water phase, or maybe sometimes it will be there in the air phase. So that means the molecule of X is continuously moving from water phase to the air phase to the water phase. But at any time, if you are going to take, the number of molecules of ammonia in this phase is constant, the number of molecules of ammonia in this phase is constant. But if you look at the concentration of ammonia in this phase, and if you look at the concentration of ammonia in this phase, the concentrations are too different. But even then the mass transfer is going to be stops. And that is what we can say, that concentration is not the driving force for mass transfer operation. The chemical potential is the driving force for mass transfer operation, which is going to be a function of a temperature, pressure, and concentration, and nature of the components. So if any one of the parameters is going to change, your chemical potential is going to change, the system is going to attain a new equilibrium. And to give you one more example for to understand the chemical potential, and suppose, let's say I have a maybe 500 grams of roses, and maybe I have a 500 grams of jasmine in your room, where the temperature is same, the pressure is same, concentrations are same. But one can see more smell of the jasmine compared to the roses. That is because the jasmine is having a more chemical potential when compared to the roses. So that is what one example I can give you. Or maybe you can think about the well-known example of your reverse osmosis process. In the case of reverse osmosis process, we have a feed solution, and this feed solution contains the water and salt. And here we have a water. Now when these two phases are there, the feed solution contains water and salt, is contacted with the water. Now what will happen? The salt wants to move from higher concentration to the lower concentration, but this membrane is not going to allow. And the water wants to move from higher concentration to the lower concentration, this membrane is going to be allowed, and now the water is going to move from this place to this place. And this process is going to be continuing. Ultimately, the liquid levels in the two layers, initially the liquid levels in the two chambers are same, but after some time, if you are going to see, the liquid level in the chamber is more, the liquid level in the chamber is less. The meaning of that, the water is moving from higher concentration to the lower concentration, and system is going to reach us to equilibrium, and this is equilibrium, we call it as a osmotic equilibrium. And if you see at osmotic equilibrium, there is a pressure difference between the two chambers, and this is what we call it as a delta pi. This is what we call it as a osmotic pressure difference. And even then, if you see the concentration, there is some salt here, there is no salt at all here, and that means it is a pure water still, but it is a salt solution. And even though there is a concentration difference, the system is going to reach us to the equilibrium. The system is going to reach us to the equilibrium, and the process is going to reach us to equilibrium, and that is what we call it as osmotic equilibrium. Then that is what we call it as osmosis. So even though there is a concentration difference, the system is going to reach us to the equilibrium. The reason is the chemical potential of, now at this stage, if you can look at the chemical potential of the salt, chemical potential of the water here, the chemical potential of the water here, and the chemical potentials are same in the two chambers, whereas the concentration are different. So what I want to tell you, what I want to impress upon you, that concentration is not the driving force for mass transfer operations. The chemical potential is the driving force for the mass transfer operations. And this is a very interesting example when you can understand. And still, if you don't understand, and when you are going to read about the thermodynamics, and the thermodynamics is going to tell us about the importance of this chemical potential, unless and otherwise you don't understand the chemical potential, one cannot do any mass transfer operations. So what I want to tell you, the thermodynamics is the prerequisite course for the understanding about the mass transfer course. Then we have a velocity. So as we discussed already, the solute particles are, the molecules are moving from one location to the other location. So it is having some sort of a velocity, and this velocity may be because of the pressure difference, or maybe because of something else. So each molecule is having some velocity, and this velocity, types of average velocities we are going to come across, and one we call it as the mass average velocity, another one we call it as the molar average velocity. In the case of mass average velocity, this is defined as u, that is defined as sigma of rho I ui divided by sigma of rho I, where rho I is nothing but mass concentration, that is nothing but kg per meter cube, where u is the mass average velocity, where mass average velocity is calculated based on the mass concentrations. So when we have a n species, species 1, species 2, species 3, species n, and this average velocity, mass average velocity of a system can be calculated taking into the molecular velocity of each species multiplied with the mass concentration divided by total mass concentration, that will give us the mass average velocity. And we are going to define another velocity that we call it as a molar average velocity. This is the mass average velocity, this we call it as the molar average velocity, and this molar average velocity is defined as Ci into ui divided by sigma Ci, where C is nothing but molar concentration, that is nothing but kg moles per meter cube, kg moles per meter cube. And now this molar average velocity is a weighted average of your based on the molar concentration. This mass average velocity is weighted velocity of based on the mass concentrations. So once if you know the concentrations, mass concentrations as well as the molar concentration, maybe one can calculate the weight fraction. This is the weight fraction is equal to mass concentration of a component I divided by total mass concentration, and maybe you can call it as a mole fraction Xi is equal to Ci divided by sigma of C, or what we call it as a C. So once if you know the mass concentration as well as the molar concentration, and one can calculate the weight fractions as well as the mole fractions, then and in the case of mass transfer operations, once if you understand about the velocity, the next thing which comes into the picture is nothing but a flux, and this flux is nothing but amount of material passing per unit area per unit time, we call it as a flux. And the flux is the most important thing that we use in the mass transfer operations. So unless and otherwise you don't understand about the flux, we cannot calculate any, or we cannot do anything about the design calculations. The flux is defined as amount of material passing per unit area per unit time. So this material may be kgs per unit area, meter square per time, it is nothing but a meter square per second. This is what we call it as the mass flux, or we may have a molar flux, kg moles per meter square per second. So we have a mass flux or we have a molar flux. This mass flux and the molar flux is given by kg meter square per second, kg moles per meter square per second. Then when we talk about the velocities, we are going to use the 3 frames of the references. And in the case of 3 frames of references, and we have a one is nothing but a stationary frame of reference. We have an observer who is observing or measuring how many molecules are passing per unit area per unit time, where the observer is a stationary. Are you understand or not? We have a stationary frame of reference. In the case of stationary frame of reference, we have an observer who observes or who measures how many molecules are passing at a given location per time. That is what we call it as a stationary frame of reference. Then the second thing is your observer is moving with the mass average velocity. The observer is moving with the, maybe he is sitting in a boat where the boat is moving with some mass average velocity, and he is now moving in the boat with the mass average velocity, and now he is measuring the concentration at a particular location. So your relative velocity is going to become ui minus u. That is nothing but your observer is moving with the mass average velocity, and your relative velocity is going to become ui minus u. Then we may have another situation. We have a molar average velocity. That means we have an observer who is moving with a velocity with a molar average velocity, and the relative velocity is equal to ui minus u. Maybe if you can put it here. So this is the stationary observer. We is moving. We is observing the flux. Maybe this is the observer. We is having a velocity that is nothing but a mass average velocity, and this velocity is nothing but ui minus u. That is nothing but a relative velocity. Maybe we have an observer. We is having a velocity that is the molar average velocity. Now this is nothing but ui minus u. So now we have three stationary frames of references, and based on that we have three fluxes, and these three fluxes, as I told you, it may be a mass flux or it may be molar flux. In the case of mass flux, we are going to denote with Ni, that is nothing but rho I. Then we have a Ji, where Ji is equal to rho I ui minus u. We have a Ji star. All these three are the mass fluxes. Mass fluxes with respect to stationary frame of reference, the mass flux with respect to the mass average velocity, mass flux with respect to the molar average velocity, rho I ui minus u. So these are the three types of fluxes that we are going to come across. That is what we call the mass fluxes. Then we have three types of other fluxes, that is the molar fluxes. And in the case of molar fluxes, we are going to designate with the capital N. Ni is equal to Ci into ui, and the capital Ji is nothing but molar concentration Ci ui minus u, where mass average velocity, and we have a Ji star Ci ui minus u. This is with respect to molar average velocity, this is with respect to mass average velocity, this is with respect to stationary frame of references. So when you talk about design purposes, we use N, and when you are talking about characteristics of any materials, we are going to use the J as small j or a capital J. So it depends on whether you are talking about a mass flux, whether you are talking about a molar flux. To tell you an example, when you talk about a fisherman, you want to catch some fishes, and he has kept his baited hook in a river. He is not worried about what is the swimming capability of the fish. He is only interested about how many fishes comes and falls in his baited hook. That is what we call it as a small n or capital N. Whereas now we have the fish, where the fish is moving against to the upstreams and downstreams of the velocities. Because of these upstreams and downstreams of the velocities, the fish velocity may be decreasing or the fish velocity may be increasing. That is what we call it as the J types of fluxes. So this N type of fluxes, the J type of fluxes, this N type of fluxes we are going to use for the design purposes as stationary frame of references, and the J types of fluxes we talk about. It will use the characteristics of the materials. So in the next class, what we are going to discuss about how we are going to combine this flux with your concentration gradient, or what we call it as the chemical potential gradient, and that is what we call it as the Fick's law. And in the next class we are going to discuss about that Fick's law. And with this I am going to stop this class. You recollect once again, we have discussed about how to conduct a mass transfer operation, and what are your design parameters, then what is your molecular velocity, then why the mass transfer is taking place, then we also discussed about how to calculate the fluxes. Then we have seen about different examples where it will use you the concentration is not the driving force, the chemical potential is the driving force for the mass transfer operations. And when you come to the next class, because this is the most important thing, unless and otherwise you don't understand about this, it is so difficult for you to understand the next class. So I request all of you to go through the materials what we have covered so far, so it will be easy for the next class. Thank you very much.